talking about his work on OpenCV. Welcome, Bo.
Hi, everyone. Can you hear me okay? Okay, thanks for showing up. I know it's the end of, coming toward the end of LCA, and we're all really tired, so I'll try to keep this as fast-paced as possible. This is my first LCA presentation, and it's also my first day of PhD candidature, so here at the ANU, so please be gentle. Okay, so today I'll be talking about lighting up OpenCV with Ne10 and Neon. So this work's been conducted by myself, Bo, Gaurav Mitra, who I share an office with, and my supervisor, Alistair Rendell. Okay, so when we're talking about lighting up OpenCV, we mean improve image processing performance for ARM-based mobile devices. And so OpenCV is an open source image processing library. And we'll talk about that more a little later on. But the interesting thing is, OpenCV has been heavily, lately, there have been a lot of Intel optimizations for the OpenCV library. But most modern mobile devices use ARM processors. And a lot of these devices have high-resolution cameras, and there are a lot of apps to perform image processing. So a lot of these Android applications or iOS applications will be using ARM processors. But the OpenCV library doesn't have a lot of these SIMD optimizations occurring. Okay, so we'll be talking about Neon and Ne10 libraries, and they're used to improve performance on ARM processors. They're not commonly used as tools by the developer, and I'll discuss that a little bit later. Okay, so the overall benefit is if we improve performance of the OpenCV library, using SIMD, we should be able to improve efficiency and improve battery life for these devices. And also, by reducing computation time, we can do more. So we can run heavier apps, do things like feature detection, or automated detection or classification of flora or fauna, or any sort of image app. When you're more creative than me, you might be able to come up with a better example. Okay, so the history of the project. It was originally started by OpenParallel. So that's a company in New Zealand. And it basically started immediately after Multicore World, which is a conference. It started every year. So it's on in 2 weeks' time in Wellington. And you should consider going. So a lot of fun. And you learn a lot from it. Okay, so it's focused on, so the project itself was originally focused on Ne10 for media processing. It ended up as a side project at the ANU, here at the ANU, in the College of Engineering and Computer Science, where we dug deeper with Neon, and I'll explain why we did that soon. So the OpenCV project was started by Intel in 1999, and it's a GitHub repository, and it's completely open source. And it's maintained by ITSEs and Willow Garage. Okay, so the things I'll talk about, I'll briefly introduce OpenCV, SIMD, single instruction multiple data, and Ne10 and Neon. And I'll briefly compare Ne10 to Neon to identify which will best light up OpenCV. So how can we optimize OpenCV for ARM-based processors? So we'll examine the structure of the OpenCV library, and basically we'll skim through the core. So there are several modules in OpenCV, and we'll look at the core module and the convert function. Image processing, there's an image proc module, and in the image proc module we'll look at binary thresholding, and we'll also briefly we'll take a bird's eye view of the filter engine. So for some of the deeper level stuff, we'll inspect the algorithm, propose a theoretical speed up from using SIMD, and we'll look at the C source and different intrinsic implementations. And hopefully, I'll convey why we should use hand code intrinsics and to give some take-home notes for the developer. Okay, so what is OpenCV? Open Computer Vision is an open source library to perform image processing. It contains about 400 commonly used image processing functions, mostly used in computer vision. And so many Android and iOS apps perform image processing using this OpenCV library. So let's make it fast for ARM processors. Again, so it's a framework written in C with a C++ high-level interface. Okay, so let's start off by what is SIMD? So single instruction, multiple data. So I'll walk you through a typical example. Say in OpenCV, without calling a low-level function in OpenCV, if you were to do this by hand, say you wanted to increase the pixel intensity of every element by 2. Okay, so we have our ordinary CPU. So this is not the SIMD approach. We have an ordinary CPU with a 64-bit register that holds one number, or we'll have 3 registers. And we'll have 8-bit numbers in RAM. So we have 8 lots of 8-byte, 1-byte numbers. And we'll fill that, so we'll have an input array. So these are some arbitrary numbers. Say there were low-level pixel intensities, and we want to improve the overall intensity by, say, 2. So we'll preload into register 2 the value 2. And then we'll perform a regular load from the first element of the input array from RAM and put it into register 1 on the ordinary CPU. And then we'd perform a regular addition. We have the result stored in register 3, and we'd have that register 3 save into the result array, the first element of the result array. We'd repeat that for the other 7 elements. And so overall, we're looking at an operation count of 8 loads, 8 additions, and 8 saves. Okay. So with the SIMD approach, single instruction, multiple data approach, and data parallelism, we have a SIMD CPU where one 64-bit register acts as 8 8-bit registers. We have our same original array, but we'll see this emulating of a register, of the 64-bit register with 8 smaller ones. So we have the same original input array. We instead of having 1, 2, we tile the 2s across the register 2. And we perform a SIMD load all the elements in one go, perform a SIMD add and store the result in R3, also over one instruction, and then do a SIMD save and save that back to the result. Okay, so overall we have an operation count of 1 load, 1 addition, and 1 save. So it's 1/8 of the operations, or an 88% improvement. Okay, so there's our drive. If we can improve a commonly used operation like this, make 8 times faster code potentially, depends on the data types we're dealing with. And faster code should imply that the program finishes quicker, and then therefore the device can idle, and if it finishes a task, it can idle, the cores will scale back, and it should save battery life. So we can improve battery life on these ARM devices. And also fewer operation cycles implies that, so if you have fewer instructions per pixel, we can improve battery life also. So if compilers can do this for you if you just use GCC or G++ -03 minus F-tree vectorize. So why should we as developers bother about looking at these lower level intrinsics? Okay, so what is Ne10 and Neon? So it's basically SIMD for from the ARM processor architecture. It's similar to streaming SIMD extensions, SSE from Intel, but there's no one-to-one mapping between SSE to Neon instructions. Okay, so Ne10 and Neon, there are intrinsic libraries. Okay, so Neon. Neon is a wide SIMD data processing architecture with 32-bit registers, 32 registers, 64 bits wide, or in dual view, you can use 16 registers that are 128 bits wide. Neon instructions can perform packed SIMD processing. The registers are considered as vectors of elements of the same data type. Data types can be signed, unsigned, 8-bit, 32-bit, 64-bit, single precision float, whatever. And they can be used with a simple hash include in your C code. Ne10, on the other hand, it's really recent. So Neon was started in 2008. Ne10, out of ARM, it was started in 2012. It's a C framework of functions made up of pre-rolled Neon intrinsics. It provides a higher level of abstraction over Neon. It's easier to use, and there's less to think about from a programmer's perspective. But there's a major limitation, or one of two. It operates only on floating point C or C++ pointer arrays. So instead of intrinsic vectors, where the programmer has to deal with SIMD registers, vectors. So that can also be included with a simple hash include. Okay, so let's try for a demo. I'll be game. Okay, so I'll basically walk you through the different approaches. So first, we'll do the same add that we followed in the first example, so adding 2 to each element. But we'll see what a compiler could do with auto-vectorization. So it'll try to develop Neon intrinsics and see how well that performs against using Ne10 to do the same operation. Ne10 with stepping, where we arbitrarily say we'll step through this many elements at a time. And we'll also look at Neon and then see how they perform running on an Android platform. Okay, so basic demo. So we have an Android JNI function called do all the things. We have return string's not important. Okay, so we'll operate on 4,096 elements at once, and we'll do this 1,000 times to give us an average sort of runtime. Okay, so these source is just setting the register. It's not timed, so it's okay. So we'll set our input source array as 1 to 4,096, and then this is how you normally do it in C. Ignore the ugly code. It's the dest is equal to the source plus 2. Okay, and we time it. This is using Ne10. We can see, so add C, float C, dest source, add 2, and the number of elements. And this Ne10 intrinsic should call a pre-rolled set of Neon intrinsics to do the operation for us. So we'll see if there's any speed up factor there. Also, if Ne10 were to operate on all these elements at once, let's try to break it up into smaller parts. So we'll say we'll try to operate on. So if our cache size, if our register size on our processor is say 64 bits, let's operate on 8-bit values at a time. So we'll step through 8 elements in one go. So we'll break it up with a for loop. So that's stepping. And then here are our Neon instructions, Neon intrinsics to do the same operation. So we can see there's a, we load 4 32-bit floats, and we will duplicate, as you saw in the initial example, we'll duplicate that, fill it with 2s across the 4, and then perform the add, and then store the result. Okay, so pretty straightforward. Let's see if... Okay, do we have the camera up? Okay, so this is a really spectacular demo. It'll take not very long, so let's have a go. So I just press the button and it'll just run through that. So this is called through the JNI, and that's it. So we can see, in this case, auto-vectorization took 32 microseconds. Ne10, with no stepping, took 28 microseconds. And with stepping, so with the extra for loop, it's 34 microseconds. As opposed to Neon, which took 13. So there's a pretty compelling case to drop looking at Ne10 right here, because if the compiler, GCC 4.6.3 can do a better job than using Ne10 intrinsics, we should really stop looking at it. So we run it again. You see pretty similar sort of results. Auto's 23, Ne10's 23, stepping's 25, and again Neon took 13 microseconds.
Can you make it any bigger?
Bigger? A bit bigger? Better? Focus. Can we see that? Sorry. Okay. Okay, so a pretty compelling case to stop looking at Neon right now, Ne10 right now. Okay. Oh, sorry. Should check that. Okay, so no more Ne10. It doesn't show much speed up, if any. Some cases it does, but only supports floating point precision. Whoops. And Ne10, as I said before, only supports floating point precision. So we should really only be looking at using Neon, as we can see that auto-vectorization in Ne10 is non-optimal when we compare it to the neonized results. So we'll look at a few different different types of test hardware for some graphs. So we'll be comparing how SSE2 compares against Neon intrinsics. Okay, so we can see we have a range of different Intel processors. We're not especially concerned with them, so we have the low-end Intel processors like Atom, and we have different latest end high-specking Intel processors like the Core i7 and i5. And we'll see out of the ARM processors, so out of our possible 10 applications, we have 6 ARM processors, and 3 of those, all the Samsungs are running Android, and the others are running Linux. And the Linux distros are compiling with, try to get it, or the standardized version of libc, and they'll be running GCC 4.6.3. And for Android, we can't be too sure, but it's a 4.6 point something. So they do a lot of heavy optimizations to the GCC compiler. Okay, and we still have 32-bit kilobit cache size L1 caches across all the devices. Okay. Okay, so OpenCV, where to begin? So Intel intrinsics. So all these SSE intrinsics have been done a lot to OpenCV already. So OpenCV 2.4.0 had 145 SSE2 functions or preprocessor operations in 30 files. And by the latest release in 2.4.3, it now has 187 functions in 55 of OpenCV's source files. So they're really big intrinsic functions. A lot of work's gone into them. So when we look at how we should be optimizing the OpenCV library, we can look at OpenCV 2.4.0. So we'll look at the history of the development, where it had 3 Neon functions in 2 files, and the latest version has 6 over 3. So clearly we, the open source community, have some catching up to do if we want to improve this open source library for Neon, for ARM-based devices. Okay, so a brief structure of the OpenCV. OpenCV has 8 major modules, including Core, ImageProc, Video, Calib 3D, Features 2D, Object Detect, High GUI, and GPU. And each of these modules are obviously concerned with different functions. So due to the size of OpenCV, let's only consider just the Core and ImageProc modules. So the ImageProc module provides a high-level image processing interface to do operations such as image filtering, but I'll talk about that more later. And the Core module. So the Core module is a compact module defining basic data structures and basic functions used by all other modules. So it's responsible, so it's the core. It's responsible for common matrix operations, vector arithmetic, data type conversions, and other fundamentals. Intel have identified 36 functions in 6 files in the core module already, suitable for SIMD. So Intel haven't made these optimizations. ITSEs may have, and other open source contributors, but we should be learning from candidates. They say these functions are really heavyweight, we should be looking at them and try to develop Neon versions. Okay, so conversion, we'll run through a simple example looking at converting float to short data types. So we know it's a computational bottleneck suitable for SIMD, as ITSEs have already developed an SSE version of it. Floating point pixel values are useful for many types, especially in image filtering. So we might do feature detection using floating point numbers, and then, but most of the data is stored as whole integers. Okay. OpenCV's SSE optimizations, again, can show us a way for ARM architectures, and we'll look at the conversion algorithm. So when we look at the conversion algorithm, we'll consider SIMD regions and peak performance, the algorithm in C, and the algorithm in SSE, porting to Neon and its performance. Okay, so this is what the algorithm looks in C, pretty typical. You want to march across the entire image and perform a saturate cast. So the saturate cast is useful for to take care of buffer overflow type conditions. So we have this saturate cast short. It'll call So we have a saturate cast short, and that'll call this one, this inline template function, which will perform a CV round and convert that float to a signed 32-bit integer, and then perform the saturate cast on the short. That's what CB round looks like, and that's the saturate cast on the short. Okay, so what's our theorized peak performance? So we have the use of Neon with dual view registers, so 16 registers of 128 bits wide, and operating on single precision floats, so 32 bits, gives us a peak theoretical speed up of 4. Okay? So this is the algorithm in SSE on the left. And so we can see a load instruction. So we load 8 bits, convert them to where are we? Yeah, so load the first half, load the second half, convert them, so we sign them from float to sign. And then we perform a packing operation which does the interweave for us. So it discards the bottom 16 significant bits. Whereas if we see the Neon version, we load 4 lots of 32. So Neon have really good data type naming. We don't get that in, so you have to be careful. In SSE, you don't really have to worry about these data types. So we load 4 by 32, then we perform a convert, so we sign it to 32 bits, and that's signed, and then we perform a vmove, so we shift to drop the lower 16 bits on each element. We do the same with the second half here, and then we do a vcombine and then a store. So then we store it as, so we combine, it's not an interweave, but we combine the 16-bit elements into one 16 by 8 vector. Okay, so operating on a 640 by 480 image, we can see that Intel, not surprisingly, are faster for most cases, but they are running at a higher frequency rate, higher clock speed, and yeah. We can see that the absolute times basically reflect on the architecture, but we can see a big difference between the auto, so auto is auto-compiled using GCC, and we're comparing against the hand intrinsics. So we can see the hand intrinsics are significantly faster. Okay, so here's just a slide of the speed up factors we're dealing with. So that's greater than theorized, but if you, we'll have a look at the assembler in a second, and we'll see that the GCC for ARM-based devices performs really badly in generating the auto-vectorization, and that's why we get this greater than theorized speed-up factor. Okay. Yeah. Okay. So basically, the SSE left is the hand-rolled, and the right is the auto GCC vectorized. And we can see that basically it's treating, aside from if you just count the number of operations, it's 10 versus 14. The auto-vectorized is doing additional checks, and it's only treating, well, it looks like it's calling SSE instructions, it's only operating on one element at a time. So we get a speed-up factor of 4. The ARM assembly is operating on eight elements at a time, and also it's 14 versus 16 operations, so there's additional checking that occurs. Okay. So moving on, so I think I'm running out of time. Okay, so the image proc module supports linear and nonlinear image filtering, geometrical image transformations, resize, affine and perspective warping, color space conversion, histograms, and much more. So any sort of image processing, basically. So Intel have identified 37 functions in 10 files with the image proc module. We'll only discuss the image thresholding section, and then we'll also skim over some other functions, namely the image filtering engine. Okay, so the image proc module, binary thresholding. So binary thresholding is the simplest form of image segmentation. There are 5 different types of thresholding operations within this function. We have We've developed Neon intrinsics for each of these functions, but we'll only consider one. So Intel have experienced SSE speed-up factors of 6, and they included in their source code, in the OpenCV source code. And also, thresholding is one of the most fundamental operations in image processing in computer vision. It's a prerequisite to a lot of different types of operations, including, say, edge detection. You might use it as a post-process to clean up the image. Okay, so we'll look at the binary thresholding algorithm and maybe some SIMD theorized performance and see whether the speed-ups match to what we expect. Okay, so binary thresholding, basically we have each element, and so this is the normal implementation. And so we march across each element in an image, and if the image is less than a certain threshold, we'll set it to 0. If not, we'll set it to the maximum possible value. So we only have 2 possible pixel intensities. Okay, so if we filled a 128-bit register with 8 8-bit values, so we'll only deal with 8-bit values. If no auto vectorization is used, so it wouldn't do any sort of optimization, we'd expect a speed-up factor of 8. So how does auto vectorization compare? So we see not quite 8 because we are using auto vectorization, but we still get a better performance boost. You'll see that the NVIDIA Tegra 3, it's running an ARM A15 processor. So we have an interesting outlier here, but it's attached to the L1. So the Neon core is attached to the L1 cache, and so I think we get a lot of discrepancies here with cache misses. So we might perform one load, and then have cache misses and wait until 4 successive cache misses and have to catch up. Whereas most of these other devices they're running ARM A8s, and they'll have it's attached to the L2 cache, so cache misses aren't such a problem. So we'll just basically go through the image proc filter engine. So when performing image filtering, it's a big engine. There's a lot of different sub-functions, and it's determined by so we'll look at the signature of what function you call, what data type you're acting on, and you drill down. So we only focus on 3 different functions: the sim row small vec, the sim column vec, and the sim column small vec. And we use Sobel, so we'll just use Sobel filtering and Gaussian blurring operations to test these functions. So I won't go over so this is the call tree. And basically it's 60%, in the call tree it's 60% sim row, and the other 40% is sim column operations. Okay, and they'll recursively poll. So it's if you were applying a separable filter, you'd do for every one column you might do for every column you'd do a row-wise. Okay, so here's the speed up we get. What's there to say about this? We still get a slight speed up, but nothing major. But I suppose if you're improving this fundamental engine, that any speed up is beneficial. Okay. One last demo. If I show you, so I'll just show you it all coming together. So this is a benchmark using, there we go. We see that? Not yet. Okay. So this is applying some of the, so it'll apply the conversion algorithm, the image proc module, but basically it'll test everything and give us our runtime factors. Can we see the text? So the average unoptimized runtime is, in seconds, 0.2 of a second, and there we are. The speed up of doing this operation using Neon it's 4.2 times faster. Okay, and we also get some binary thresholding, so we'll run through different types of applications. So runtime in seconds, 0.04 of a second, and we get a speed up factor of 1.7. So this should go with the results in the table. Okay. Keep going. Let me see. Okay, so summary. We see that using Neon reduces instruction cycles. Whoops. Wait again. Okay. Which should improve battery life. It certainly improves performance and frame rate if we can do more of these operations per second. OpenCV is a big library, and ITSE's OpenCV, as the OpenCV maintainer, has started neonizing functions, as we saw before, but we really have some more work to do. It's an active area of interest. There's ITSE's Tegra optimization paper. They're not releasing any of these optimizations as open source, but they achieve a lot higher speed-up factors, but they're also using proprietary tools by NVIDIA. Okay, so some take-home notes. You should always compile with GCC and G++ -03. Even though it increases the binary size, we should get faster speed-ups. You can use profiler tools to identify critical code sections. We don't always have SSE intrinsics to show us the way to how we should be performing SIMD for ARM processors. And Ne10 may speed up bottlenecks. We didn't see any there. Sometimes it's tiny, so they're about equivalent. But it does force vectorization, and it helps restructure the program for a problem for a programmer without going straight into the intrinsics. It can be quite a jump. However, when efficiency is paramount, we can't overlook Neon. And it's impractical to neonize everything. It's time intensive to restructure all our C code to Neon, but we should be smart about what bottlenecks we do develop Neon for. So all our results can be validated by running these Android apps, available both on GitHub under the Open Parallel website. And again, all runtimes were generated with GCC 4.6.3 or the Android at 4.6.x with -03 and and F3 vectorize. Okay, thanks. Are there any questions? I thought I was running over time, so.
You said earlier on, was it the Ne10 or the Neon, the other one had only floating point support?
Yeah, only floating point.
Yeah. So if you do it, you get double precision when you use your method. Have you done any experiments to see what speed ups you get with double?
Not really. No, I haven't done any tests there at all. No. I think Ne10. I believe that Ne10 has support for these the double precision floating point values, but haven't compared any yet. Anyone else? No? Okay, good. So I guess we started over time from technical difficulties, so I guess stop here. Thanks, everyone.